I'm going to show some skills that the robot learns to do autonomously. So the first one is cooking. So the robot can actually cook the shrimp. And it also can be learns to like navigate to a elevator and then go inside, press the buttons. You can also deal with liquid, which is transparent, and do the wiping. You also can interact with humans. So in this case, we're playing high fives with the robot. Today, I'm going to talk about advanced in using machine learning to make better robotic systems. I'll focus on two systems. One is robot parkour. The second one is Mobile ALOHA. Like many people, I was impressed by the performance of AlphaGo, like how a software system can be designed to learn from massive amount of trial and errors without too much programming. And that's where I started my robotics journey from reinforcement learning. But reinforcement learning in the real world can be tricky. We have seen that people have tried to make many progress by using reinforcement learning training and then deploy it directly in the real world. And there are many recent advances in this domain, including PCB insertion and also mobile manipulation. But there are many limitations. So usually people restrict the observation space and action space in order to make reinforcement learning in the real world work because of the sample efficiency problem, and also because trial and error can break things, and also it's kind of usually pretty slow. At the same time, simulation is getting better. So on the left, I'm showing the ice environment simulator created by NVIDIA, and on the right is Mojoko. So people start to think like, if real world reinforcement learning is hard, why don't we just use simulation as a tool to sample efficiently and train robots? And many people start to realize that and think if simulation gets better and better, faster and faster, a lot of core problems can be solved, including acceleration. In the past, I've tried using reinforcement learning for various tasks of like locomotion, including training adaptive policy for robots, and also using reinforcement learning to get different gaits of Lego robots, and also combining vision and proprioception for the navigation of kind of long horizon tasks for Lego robots. And also, reinforcement learning can be used to train robot dogs with arms attached on the back, so it can like do these kind of whole body tasks. The first robot learning system I'm going to talk about is robot parkour learning. So why are we concerning about like parkour? Isn't like walking robots good enough? We think it's not enough. Because we think parkour skills are actually necessary for the open world. So there are many kind of real world scenarios that requires the robots to achieve this kind of extreme agile skills in order to like overcome these kind of environments in the open world. So on the left, if the robot can leap, it can leap over the gap. If the robot can climb, it can overcome this kind of high barrier. And even indoor, if the robot can crawl, in this case, in a cluttered indoor environment, the robot can like go beneath the coffee table and then reach the other side. I'm showing some example of the behavior here. So this one is leaping. The robot can also climb another robot. It can also do this kind of crawling behavior. Because it's using the depth information, it can also climb in low light. Here's another example. It can also like tilt itself to squeeze through narrow passes. To kind of like shrink the width of the robot, to pass through a pretty narrow gap. So the reading success on locomotion mostly rely on heavy engineering. So I show 3 papers. All of them are using, more than 9 terms of real world terms in order to get a single scale to work, which is walking. Because of that, it's kind of not scalable to training all the parkour skills at once. So if we kind of want to get 5 or 6 parkour skills, we kind of need to design 6 or 5 sets of this kind of heavy reward engineering schemes, which is pretty hard and pretty not scalable. So we're thinking about like how to solve this in a scalable fashion. One inspiration we take is from a classical method called direct collocation method. By default, like in simulation, we kind of ensure that the robot is doing hard dynamics constraint, which means that the robot should not penetrate onto this kind of obstacles. But with our pipeline, which is reinforcement learning with soft dynamics constraint, the robot can actually penetrate obstacles because we don't enforce the hard dynamic constraint, but instead we let the robot to have a soft dynamic constraint with the environment. Concretely speaking, the robot can actually, softly penetrate the obstacles, and we penalize that. So if the robot penetrates the obstacles where it shouldn't be, we kind of penalize the penetration by specify that into a word term. So we measure the number of penetration points, which we sample on the collision bodies of the robot. As we can see on the left, we kind of sample different points on the robot. And you can notice that we sample more points more densely on the kind of the hip of the robot to ensure that it can not bump into that position because there's a lot of motors and delicate parts in that region. Because of that, we specify the reward and the robot can gradually learn to obey the physics by not penetrating the obstacles. By using this technique, we have only 6 reward terms in total for learning all the parkour at once. So together with reward term encouraging the robot to move forward and 2 reward terms encouraging the robot to save energy, we kind of get all the parkour skill at once. This is directly training with soft dynamic constraint. At the start, the robot just ignore the obstacles totally. And then gradually it learns to kind of try to not collide with the robot, not collide with the obstacles. But still, you can see that a lot of time, the robot actually penetrates through parts of the obstacles. At the end, it kind of gets it and train as hard as possible to not overlap with the obstacles. But the stage 1 is not enough because with real physics, the robot still, especially for the climbing skill, it doesn't really get the physics correctly. So we add an additional stage for fine tuning. So after we train with the first stage of soft dynamic constraint, we turn on the physics, actual physics, and the robot is fine-tuned in this environment with using the same reward term. In order to deploy this policy that we train in the simulation, we need the robot to actually select the skills by itself and condition on using its own egocentric vision. We don't really want the robot to use motion capture, LiDAR, or heavy compute because we want to deploy it on a pretty off-the-shelf robot dog. So together, this is a neural network architecture that we use. So the egocentric depth is first processed by CNN together concatenated with proprioception. So the proprioception includes the joint angles of the robot and also the direction of the robot. So these are the things that the robot can feel when basically humans can feel basically when humans close their eyes. And together with this proprioception, we concatenate it with vision and pass it to a GRU. So the robot has memory about the environment.
Zipeng, I see a question. Does the robot not get climbing with soft physical constraints because you can't model gravity properly with soft physical constraints?
I think that's true because with the soft constraint, the robot cannot actually, use, the top surface of the obstacle as a standing point to support itself. But like after fine tuning it, it gets to use it.
Just to clarify that I'm also following this. You guys do this in simulation, and then you try it on real world, and also that way
Yeah.
you collect the data samples and you fine tune. Is that right?
No. So everything is done in simulation. So the fine tuning is also done in simulation. So we kind of turn off the physics during this first stage and turn on the physics during the second stage of fine tuning. And in this kind of fashion, we kind of relieve ourselves from heavy reward engineering, because the first stage is pretty easy to solve gradually, and the second stage, although it's pretty hard to solve, is pretty easy to solve with the initialization from first stage.
I see the follow-up question to the previous one. What if you allowed the agent to choose hard or soft constraints in the environment?
That's a good idea. We haven't tried it, but maybe it should work. We deploy this aggregated policy on a real robot, and as we can see on the top right, it's a vision of the robot which is steps, and the robot can do all the skills at once. So we also did some quantitative studies on our policy in the real world. So the robot can actually climb obstacle that is higher than itself and leap over gaps that is longer than the body length of the robot, and crawl beneath obstacles that is lower than the robot height of itself, and tilt to squeeze through narrow passes, narrow places to that is actually narrower than the robot width. By using parkour skills, the robot can be much more powerful. And we're also seeing, because we are using a one neural network that takes in images and as input and output the action and runs at fifth years, the robot can actually have some retrying behaviors. If the robot fails at the first attempt, it will push push itself back to increase the clearance, to have a larger run-up space for the subsequent trials. We open source everything, including the training code, the simulation code, and hardware code, and also the checkpoint weights of our neural network on the GitHub. We did a live demo at Corals last year, and it's pretty fun. There are many actually failure cases. So if the robot is trying to leap low friction surfaces, it cannot really leap over a large gap. If the obstacle is pretty high, then it cannot climb it, mostly due to the limit of the motor, because it cannot exert forces that is large enough to push the robot to that high. And because we are using a rigid body simulator, it is pretty hard for it to deal with deformable objects. These are concurrent work that people also tried to learn parkour skills. And feel free to check them out. And these are pretty good work, and a lot of different kind of skills have been shown in these work. This is for their website. Parkour and locomotion is pretty fun to work with. But is there a way to make the robots useful, especially the mobile robots? So one direction that we can try is put an arm on top of the robot and make the robot solving mobile manipulation tasks. So if you're trying to do manipulation, can we use simulation? Because usually manipulation requires semantic information, which cannot just rely on RGB, cannot just rely on the depth information or point cloud, because these are mostly geometric information. And also in the simulation, soft objects are pretty hard to handle. There are many efforts in NVIDIA trying to push in this direction, trying to reproduce all the semantic information and RGB rendering and soft object rendering in the simulator. But meanwhile, people have I think there's a huge trend in the robotics that people are using human demonstration in the real world and using imitation learning as a way to teach a robot to doing all kinds of manipulation skills. So these are two cool projects from Google that people teach robots to do all kinds of manipulation tasks by using human demonstration collected directly in a robot. People are starting to think that maybe if we have lots of demonstrations, basically lots of data to supervise training the robots, maybe we can solve the robotics in one day. How do we train policy? There are two parts. It's unlike most of other domains in AI, like computer vision or natural language processing. The data sets are usually you can download it from the internet. For robotics, there's no such kind of huge data set for people to play with. So data collection is definitely important. So we have seen a lot of progress in this domain. So this is a project called ALOHA that led by Tony that actually a pretty low cost hardware system can be used to accurately teleoperate the robot to collect the human demonstrations for robots. And also it's a by manual setup. The second part of training a policy using imitation learning is can we use the data efficiently? So these are the two methods that people have shown in the past that can be used to efficiently train a policy to let the robot directly learn from human demonstration. On the left is transformer-based architectures. On the right is the diffusion-based policy led by Chen. So one key idea that's pretty important in both of the papers is that people are using action chunking. So it's a technique that trying to let the policy instead of predict one action at each time step, the policy predicts a short sequence of actions for the robot to execute into the future at once. So by that, 2 Hertz policy inference can, with action chunking size of 25, can lead to a 50 Hertz control. So by this kind of shrink the long horizon problems in manipulation by a pretty large factor. So one idea is that I have in the past is maybe we can just use Aloha as a platform and make Aloha movable, so Mobile ALOHA, and put the Aloha setup on a mobile base and use it for mobile manipulation. So this leads to the project called Mobile ALOHA, and we're trying to build bimanual mobile manipulation setups and including the data collection and efficiently learning pipeline for the robot to learn from the data collection, from the human demonstration that we collected during data collection. So this project is led by me and Tony and advised by Chelsea. So this is the robot that we built. So by mounting the Aloha setup on mobile base, and also tether the human to the mobile base, we can collect the whole body data, motion data information, including the motion of the arms of the human, and also motion of the base of the human. So it can record the speed of me moving forward and moving angular, and also the motions of the arms. So everything is on board. So the robot is not tethered to a cable, so it can move freely.
How many hours did you spend on this? Just basically, like, what is the reasonable size of data samples you guys need?
Yeah, we will talk about this. So basically 50 samples for each task. We found that's pretty good enough with a technique that we'll introduce later. Yeah, so this is the data collection pipeline. So on the left, we showing the teleoperation phase. So we kind of attach the leader arms that the humans are using to puppeteering the front 2 main robot arms. But like during deployment, everything is just controlled by a new network. So we can just remove the second half of the robot, so the robot can be more compact during deployment. Some key aspects. So the robot has 14 degree of freedoms on the arms and 2 degree of freedoms on the base. So for the base, it's like moving forward and also moving angularly. the weight of the robot is 75 kilos. Although it's pretty heavy, the resistance for the human teleoperators to push around the robots is pretty lightweight. So we measured the rolling resistance on a normal floor. It's just 13 newtons. And we did some user studies. We found that Mobile ALOHA is pretty like easy or user friendly. We kind of asked a bunch of people, and in this case, it's 9 people, to 8 people to perform a task, and they haven't like used the Aloha Mobile ALOHA setup a priori, so they have no prior experience about teleoperating this robot. But after 5 trials, we have found that the average speed of time to complete the task is kind of approaching the accurate speed. So the accurate speed in this case is the speed of me and Tony. So yeah, so this kind of shows that the Mobile ALOHA setup is pretty easy for people with no prior experience with Mobile ALOHA, and they can just pick up the setup and learn how to use it. And we open source the hardware, so including the CAD design, the how we find different parts. Yeah, so people are starting to use it and build different kind of models from it. We don't have collaboration with any companies, but like the different robotic company are selling the kind of their versions of Mobile ALOHA, and many of them are selling a lot of orders worldwide. So that's the teleoperation, the data collection part. After we collect the human demonstrations, we kind of need a pretty good algorithm to learn from the data. So this is a general network architecture that we use. So it's like an encoder decoder transformer based model. So it takes in 3 images, including the back camera, which is the first images, and also the left and right wrist cameras, which is the second and third images. By like taking this RGB information and also the joint informations, kind of go through a transformer encoder, and then it's kind of passed to a transformer decoder. The decoder decode a short sequence of action sequence. So this is like a hyperparameter that we can specify. So how large the actions chunking size should be. This kind of depends on the task. And also we tried diffusion policy and VIN. So these are the 2 other imitation learning methods, and they also work for our Mobile ALOHA robot. So I'm going to show some skills that the robot learns to do autonomously. So the first one is cooking. So the robot can actually cook the shrimp. And it also can be learns to like navigate to a elevator and then go inside, press the buttons. You can also deal with liquid, which is transparent, and do the wiping. And also can interact with humans. So in this case, we're playing hi-fi with the robot. And it's kind of robust to defend closest and height of humans. So we can rinse the pan. So this is an interesting task. So we only collect the data for the robot to push the chairs inside for the first 3 chairs. But surprisingly, when we deploy the robot, it tries to generalize out the distribution to the last 2 chairs, even though I haven't seen last 2 chairs during training.
It seems it did a good job, right?
Yeah, so we hope it can do that, but it's kind of surprising it can generalize auto distribution. And it can also like open the cabinet doors and put a pretty heavy pan, in this case 1.7 kilo pots, using its manual manipulation skills, and put it inside the cabinet. So how do we like achieve the pretty good data efficiency? As we mentioned, we kind of just use 50 demonstration per task. We use a technique called co-training. So because we have a pretty large data set for the static ALOHA, which is ALOHA mounted on the tabletop, we kind of just use that as a co-training term for the policy to generalize better. So in total, we have 800 demonstrations from the static ALOHA dataset. Because the static ALOHA dataset doesn't include the motion data, like the base of the static ALOHA is not moving. So we just simply put zeros for the base action for the static ALOHA dataset. And surprisingly, it works pretty well at the first trial together with the Mobile ALOHA dataset. And yeah, so for each task, we collect 50 demonstrations. And it takes about, usually half an hour to 1 hour for a human to collect the data set for one skill for Mobile ALOHA. We found, like, quantitatively speaking, co-training improves the performance, especially for fine-grained tasks. If we see, if I ask the robot to, lift the glass and do the wiping, or ask the robot to, turn on the faucet. So these kind of tasks requires pretty, precise action for the robot. Then co-training helps complete these kind of difficult tasks by a large margin. Our pipeline is compatible with all the state-of-the-art imitation learning methods. So we tried ACT, diffusion policy, and also VNN plus action chunking. So we saw, like, across the board, co-training in general helps different kind of training scheme, different kind of imitation learning methods. Co-training also improves the data efficiency because, like, we incorporate a large data set from static ALOHA for the co-training. It helps generalization quite a bit, even during the low data regime. So if we just collect 35 demonstrations of Mobile ALOHA, and by using co-training, we can boost the performance from 30% to 70%. And also co-training, like in the past, people kind of need to specify this kind of co-training proportion, co-training sample percentage, if they use a technique. But we found in our pipeline, co-training is pretty robust to how we sample from the co-training dataset. So we try to sample like 30% from the static ALOHA dataset, or 50% or 70%. All of them yield similar performance. And we found co-training kind of outperform pre-training. So by pre-training, I mean training the policy first on static ALOHA dataset, and then fine-tune alone on the Mobile ALOHA dataset. We found co-training improved the performance quite a bit. We suspect it's kind of due to the small size of the Mobile ALOHA dataset during fine-tuning. So the pre-training plus fine-tuning technique doesn't work quite well. So after we're using the technique, the robot can robustly complete different tasks, like continuously. So on the left, the robot can complete the wiping task now in trials autonomously, and robot is trying to do put the pot into the cabinet after opening it pretty robustly, even though we have like throwing all kinds of visual distractors into the scenes. We release all the code, including the hardware code, which is for the data collection, and also the learning code. So we put everything on GitHub, including also the Git histories, so people can take a look and try to see what things we have tried but failed. In summary, these two projects made me to think that robotics is like a system engineering. So it's not just perception, also the control part. Also, I have different tasks for robots. So the robot can move, the robot can manipulate. And especially in the mobile project, we think that the hardware and software co-design, co-optimization are pretty important. Robotics definitely needs pretty good data engineering to where I've shown that simulation data can be helpful and imitation learning using real world human data can also be pretty useful. Human data, no, human demonstration. So they're also like not just active data sets, but also passive data sets people collected, for example, on the YouTube. So we mostly focus on the robot data for now, but there's massive amount of data for like recording human doing all kind of stuff. So if there's a way to utilize that, it will be super fun. Yeah, so that's the end. Thank you.
Awesome. Thanks a lot for your presentation. So I see a question from Kojo.
Yeah, I think my original question was answered, which is how robust is it to changes in the environment? I'm also wondering, like what's the level of effort involved, do you think, to port this to like different hardware that's not like the original, so say like different um, robotic arms than the ones you used?
It's kind of robust to the like visual distractors, but like if we just trying to put the robot after training, like after data collection in one environment and switch it to a totally new, like new kitchen or new environment, then I don't think it will work because everything is different. Like the floor, the environment, the objects, uh, even the positions of different kind of objects are different. So I don't think that will work. Um, but like it's the robustness right now is kind of limited to the visual distractors. Um,
Right.
and also for the second question, how like this pipeline can be transferred to, different platforms, different robot. Uh, we found puppeteering is a pretty important way to collect high quality manipulation data in the sense that it allows us to, accurately teaching the robot to, using the robot to collect the human demonstration. There is a project called Jello that kind of build this kind of puppeteering teleoperation system for different robot arms, including the Franca Panda robot arms, including the UR uh, robot arms. So feel free to check that out. And I think that will like speed up the data collection speed up the high quality data collection by a lot. So the project is called Jello, Gell.
Zipeng, I really appreciate the talk. I wonder if you're familiar with laundry folding task. I know that there was a Tesla video which was faked earlier in the year, and there's another contender that claims to have solved laundry folding called Eve. And just in general, what's your favorite really hard task that you have your goals?
So first of all, I think the test about demonstration is not fake. So it's trying to demonstrate the hardware capability by using teleoperation. Even building the teleoperation system and the robots is like tremendously hard in the sense that you kind of need to be accurate, need to be real time, and also transporting all the kind of sensing from the robot to the humans, and also the visual delay should be very small in order to do the like pretty good laundry folding and stuff, including the flaying the clothes. But yeah, so for the robotics task, I would think like laundry folding is definitely hard because it requires if it can do autonomously, not the teleoperation part. If the robot required to do like laundry folding um autonomously, it's pretty hard because of the diversity of different clothes, different trousers. Um, so things like that requires a pretty good understanding about um, the clothes that the robots need to deal with. Um, so this is like mostly focused on the perception part of the robot, um, like complexity. But for the control part of complexity, I will say that even PCB insertion, like stably insert different things into a PCB can be a pretty hard task.
Yeah, another question. So I think you started off with the simulation, learning in simulation, and then you covered learning with imitation. Um,
Yeah.
have you explored like or plan to explore like fusing those two? So learning simulation and then also imitation.
I'll say imitation learning has a benefit of, no, it just collect data sets in the testing environment. If things work, it should work. There's no, same to real gap. And also the RGB rendering is real. Like we basically collect RGB images, like video flows, um, in the real environment. But collecting them can be time consuming. So simulation can be a pretty good, pre-training stage, for something to work. That we can like use a small data set to fine tune, the pre-training checkpoint, by using the small like real world data set that we collected.
Yeah.
That's my general thought. Like,
Mhm.
I think simulators are also improving, and real world data collection pipeline is also improving. So, maybe we can just throw all the data, into a one data set pool, and things maybe work magically in the future.
Other vision algorithm used from OpenCV or some other new algorithms were used?
Oh, for the algorithm, we just train end to end. Let me pull out the slide. Yeah, so it's just taking like first pass through the TN and then, tokenize it, because we're trying to put everything into a transformer. And yeah, and it's like theater, like object detection architecture that we use. It's pretty similar to that one.
And
And
what's
yeah,
the camera resolution?
oh, camera resolution is about 480p for each images. For each image is 480p.
I see a question from Eric. How close are we to having the robot learn on their own by watching and imitating humans?
Oh, that's like I think grand challenge of robotics. So people are trying that, but like there's no good results.